So we're going to start worksheet 14. So let's read the first problem here on the worksheet. So it's a somewhat of a qualitative problem. So worksheet 14, problem 1. Let's here is the circuit. You have got a switch here. We have an inductor. We have a resistor. Resistance is R. The battery has an EMF. The resistance is 2R. Yeah, 2R. And then you have another resistor here. This is inductance L and then 2R. So the first question is, as soon as you close the switch, okay, so let's close the switch at t equal to 0. We're going to close the switch. What did we say when you close the switch? Initially, what's the current through the inductor? No current runs through it initially. So that means any current that you have at t equal to 0 will go this way. Will go from the battery through this 2R through the other 2R. That means basically you have a circuit where you just don't have this branch. So it's like 2R and 2R are in series. Okay? Does that make sense? So you have these two resistors are in series. So what's their total resistance?
The sum of their inverse.
Yeah, in parallel it would be the sum of the inverse.
Oh,
right?
I'm sorry, yeah.
Yeah, it's just the sum, right? It's just 4R. So therefore the current initially at t equal to 0, the current will equal to the EMF voltage over the total resistance, right? So over 4R. That's the current. So which option is correct? What's the current through the inductor? I1? 0. And then the current through the bottom resistor is this, right? So it's option A, right? That's correct. So A is correct. Okay. How about part 2? After a long time, what do we know about now the inductor? After a long time, does it? The current now stabilizes, right? You'll have a constant current. See, the inductor resists change. So at t equal to infinity, after a long time, the current now has constant value. It's no longer changing. So what happens is, the inductor simply becomes just like a wire. So now, will there be any current running through the 2R? No. Because the current would just go this way, right? Because I mentioned before, you can use the loop rule. You see that you go from here to here. Let's say you go from here to here, you drop by a certain current, and then you go from here to here, you increase by the EMF. There is no change here, so you just get 0. So this one actually has 0 voltage across it at t equal to infinity, so no current. Another way to view it is, at t equal to infinity, the current comes this way, it gets to this junction. What's the resistance of the inductor at t equal to infinity? 0. So it has a path where there is no resistance, and it has a path where there is some resistance. Why don't we go through the path that has 0 resistance? So all the current goes through here, nothing goes through here. So basically at t equal to infinity, you just have this circle. This loop. So what's the current through that loop? Through the upper loop. What's the current?
E over 2R.
Yeah, E over 2R. So in part 2, the current would be the EMF over 2R, and it is the current that will be going through the inductor. How much current will go through the 2R, the bottom of this one? 0, no current. So which option is correct? D, right? Yeah, D. D is the right answer. What was for part 1? For part 1 it was, I think, A, right? Yeah.
Could you explain again how the current in the first loop is 0 for part 1.
For part one or two?
Part 1.
Oh, for part one, yeah.
Yeah.
So we mentioned initially, the current through the inductor has to be zero, t equal to 0. And I mentioned this in class. Imagine it's some value, right? Imagine, so that before you close the switch, it's nothing. And then after you close the switch, it's some value, right? So basically the energy in the inductor is 1/2 Li squared, right? The energy would go from 0 to some number in no time. So that means you have an infinite power. Because energy per unit of, the change in energy over time, right? The energy is 0 and then it jumps. So that's an infinite slope. So do we have a source that gives us an infinite power? We don't, because if it's I, the power through the battery, or the power from the battery is just the current times the voltage of the battery. So it's just, that's not an infinite number. So it has to start from 0. So for an inductor, always the behavior is this. For an inductor, the current always starts from 0 and then asymptotically approaches a certain constant current. And it's, I mentioned also in class, an inductor is the mirror image of a capacitor. An inductor at t equal to 0 is like a capacitor at t equal to infinity. Because at t equal to infinity, a capacitor would be fully charged, right? And wouldn't allow any current through. The inductor does that at t equal to 0. And then a capacitor at t equal to 0 will allow all the current. It's like it's not even existing. It's just like a wire. The same thing done by an inductor, but at t equal to infinity. So they're just mirror images, basically. Okay. So what an inductor does at t equal to 0, the capacitor does at t equal to infinity. And what an inductor does at t equal to infinity is what the capacitor does at t equal to 0. Let's see. Okay, let's go to problem number 2. Problem 2. Here's problem 2. You have for problem 2. You have your inductor, you have your resistor, and you're told the following. The current is going this way, right? Current going that way. So let's apply the loop rule, if you like. So what did we say? The change in potential when we go across from this end to this end. In the inductor. What was it?
Negative L dRdt.
Thank you. It's minus L times di dt. That's the change in potential from here to here. If you go in the direction of the current, right? We said going in the always go in the direction of the current, and it's minus L di dt. So let's go through the resistor now. So the current goes this way. We're going still in the direction of the current. So what's the change in potential across the resistor? It's IR. Is it plus or minus? Huh?
Minus.
From here to here, yeah, you go from higher to lower. So the change will be the lower minus the higher, so it's minus. So it's minus IR. And we completed the loop, so 0. Alright. Okay. And so let's solve for the dt. So you got this, the dt equal to minus R over L times I, right? So move to this side and divide by L. So that's the dt. So which option is correct now for problem 2? D, right? Yeah, D is the right answer. And we did this in class. Remember, we solved this, and in fact, let's solve it right now. You would have the current, therefore, will equal to I0, whatever the current was initially, and then e to the minus R over L times I, right? That's the solution to this differential equation. So that was part one. Let's look at part two. I'll do that here, part two. The current as a function of time is this, right? As a function of time is that. So what's the current when the time is equal to L over R? So what does this mean? This is not correct, right? What did I? T, yeah, not I, T, yeah. Just realize it. It should be time. So if you plug in T equal to L over R, what do you get? You will get I is equal to I0 e to the minus R over L times, what's the time? What did we say? With what? L over R. So what is R over L times L over R? Yeah, just 1, and there is a minus sign, so you get just I0 e to the minus 1. Now what is e to the minus 1? How much is e to the minus 1? So should be 0 point something, and then you got the I0 here. So what is e to the minus 1?
37.
Huh?
37.
0.37, thank you. So which option is closest to 0.37? Yeah, 0.4 is closest, right? C. I'm sorry? 2 part 2? Yeah. So it's 0.37, so the closest is 0.4, right? So it would be part 3. Oh, that's part 3. Oh, so what's part 2? What do they want?
You already did part 2.
Isn't it just the
Oh yeah, so that's the answer to part 2, right? Yeah, okay. So I guess skip part 2 somewhere. I didn't see it. Yeah, there is part 3. Okay. So we did part 3 then. Okay, so that's good. So we're good up to this point. So let's, can I erase this board? So let me erase the board, and let's please read problem 3. So in problem 3 it says, in the circuit shown above, it's actually to the side, right, not above, an ideal inductor of inductance L is connected to a resistor R. So just like we had in the previous problem. So the first question, let me pay attention here. Yeah, we have part 1, 2, and 3, and 4 in this case. Okay, all right, so I'm just making sure. So here is the inductor. Here is the resistor. Inductor, resistor. That's the current. So the current goes like that, right? Well, counterclockwise. Okay. Now they're saying, what happens to the energy in the inductor? So part 1. Remember, what's the energy in an inductor? What did we say? Oh, right here. 1/2 Li squared, right? The energy in the inductor is 1/2 Li squared. So U 1/2 L times I squared. Now, does the inductance change? No. The inductance, once you make an inductor, it has a certain inductance, right? So the inductance is constant. So what's happening to the current then? Is the current same, changing, getting bigger or smaller?
Changing.
Changing, but getting bigger or smaller?
Bigger over
Okay.
Decreasing.
Huh?
Decreasing.
Decreasing? Okay, so who wants to tell me why it's decreasing or why it's increasing?
The resistor is taking the charge out of it.
Okay, so it's decreasing, you would say? Yeah, it's decreasing, right? We just wrote this formula. I is equal to I0 e to the minus L over R or R over L?
R over L.
R over L, yeah, because L is ohms times seconds here, so, yeah. So, it's decaying, it's becoming smaller, the current is getting smaller. So if the current gets smaller, what happens to the energy? According to this formula. Yeah, the energy is getting smaller, yeah. So for part one, oh, I'm sorry, so part one is to write that formula, right? Yeah, somehow I'm missing parts in this. Okay, so part one is this, okay, fine. So part two is, what should we say? Increase, decrease, or stay the same?
Increase.
Huh?
Increase.
Increase, the energy gets larger or smaller?
Increase.
Smaller, right? Yeah, the current is decaying. So the energy will actually get smaller because the current is getting smaller. So it's decreased. It decreases. Is it clear why it's decreasing? Right, so you're losing current, so it's decreasing. You're losing energy. Where is the energy going to? To the resistor, yeah, you're losing it as heat. Inductor loses energy, resistor is using that energy. Maybe your resistor is a light bulb, you're getting some light out of it, or some heat. Okay, let's go to part 3. It says here, which of the following statements about dB dt, the rate of change of the magnetic energy, and I squared R in the resistor, what's the relationship between them? I mean, is dB dt bigger than 0 or smaller than 0? What did we say? Yeah, it's decreasing, right? We said this energy is decreasing. So if it's decreasing, its derivative should be positive or negative? Should be negative, yeah. So for part 3, du v dt, they're asking, is it the plus or the minus of the I squared R? Well, think about it. R is always what? Positive quantity, right? Non-negative. R cannot be negative, right? Just the resistance. Squaring the current is always what? Positive. So to ensure that this is negative, what should I do? Choose the plus or the minus? Clearly the minus, right? Yeah. Minus. Okay. Now it says, use your results from parts 2 and 3 to obtain an expression of di dt in terms of R, L, and I. Okay, well, we want di dt. Let's do part 4. So let's take the derivative du dt. This du dt. So take the derivative of this, right? Du dt. So you have d dt of 1/2 Li squared equals, on the right side you have minus I squared times R. So take that derivative. Are we taking the derivative? Well, can someone tell me what the derivative of this will be with respect to time? So you would have, yeah, L times I. The 2 comes down, right? Cancels the 1/2, but you're not done. If you were taking the derivative with respect to I, you would be done, but you're taking the derivative with respect to t, so you have to use the chain rule to put di dt. in here you have minus I squared times R. So, cancel I, and you have di dt equals to minus R over L times I. Is that clear? So I want you to, after you write this one down, take a look at problem 2 and tell me what we had for di dt in problem 2. What was di dt in the previous problem? The same thing. So that's the point of this exercise. You can use energy considerations to basically do the same thing. Yes, thank you.
How did we get di dt again when we took the derivative?
Yeah. You got the derivative is not with respect to I, it's with respect to t, right? I is a function of t. So when you take the derivative, you have to take the derivative with respect to I, and then times di dt, because of the chain rule. Yeah. So, does that make sense?
Yeah.
Okay.
Thank you.
Okay. Yeah, you're welcome. Okay, let us read problem 4. There is an introduction to it, and I let you read problem 4, and then we will go through it. So we have the following. So you have this circuit here. You see it's open here. There is a switch that you can either connect it between here and here, or here and here. So it has been this way for a long time. So basically this inductor is not even part of the circuit yet. Not part of the circuit, it's not connected. So what do we conclude about the capacitor now? Is it charged or not charged? Huh? Not charged because? How would the current flow?
Is the inductor or the capacitor?
The capacitor.
Go to the capacitor.
Like this, right?
Yeah.
Yeah. So there would be, what kind of charges here? Pluses. And here it would be minus. So if you leave it for a long time, the capacitor will be charged, right? So we have a inductor. The inductor, nothing is going on. Capacitor is charged. Okay, so we got this. Pluses, minuses. So now you take this switch and you flip it to here, which is this. Okay, flip it there. So you have pluses here and minuses, right? So what happens now? Current will start to flow this way, right? It will climb from 0 and then it will start to flow this way, and then flow back. So now, how about this branch now? Is that part of the circuit? No, it's disconnected, right? So you can basically disregard. It's like you have this. So you can just like this. Faster, you have an inductor, right? This part now is cut off, not connected. Okay. So let's read through our options. So it says the switch has been in position A for a long time, and then the switch is moved to position B, right? So we got this situation here. So at t equal to 0, how much current will run through the inductor the moment you connect it to position B? What do you know about inductors again? How do they behave? They would oppose the change. So the current has to start from 0 and then grow, right? So the question is this: when the current, let me see, after the current through the newly formed lower loop rises to some maximum value, so the current starts to increase. At the instant when the current has its maximum value, which of the following statements is or are true? So the current is what? Maximum or minimum? What did we say? Maximum. Okay, good. Current would be maximum. So it says here, let's look at the options. The charge on the capacitor will have its maximum value. Charge on the capacitor, no, yeah, false. Because the capacitor here, the moment you flip it, it was fully charged and it starts to discharge. The capacitor will start to discharge and the current will increase and increase until the capacitor is fully discharged. Here's another way to think about it. Initially, where is all the energy? Initially, it's in the capacitor. There is no current running through the inductor, so the inductor doesn't have any energy. When the current is maximum, the energy in the inductor is what? Maximum or minimum? The energy in the inductor. What's the energy in the inductor? It's this, right? 1/2 Li squared. So it'd be maximum. Well, where did all that energy come from? It came from the capacitor. It doesn't come out of nowhere, right? The conservation of energy. So the capacitor loses energy, it goes on the inductor. Therefore, the capacitor will not have maximum charge. In fact, it will have minimum charge. It will be discharged. There will be no energy in the capacitor. All the energy will be in the inductor. Okay. So option 1 is not correct. It's wrong. Let's look at option 2. The magnetic field in the inductor has its maximum magnitude. What can we say about that? Do we agree? Or the magnetic field is maximum. So we said the energy in the inductor will be maximum, right? The energy in the inductor will be maximum because the current is maximum. How does an inductor store energy?
Magnetic field.
In a magnetic field. So what can we say about the magnetic field? It's maximum. Yeah, it's maximum. So the magnetic field actually has its maximum magnitude. How about option 3? So option 2 is correct. How about option 3? The electric field in the capacitor has its maximum magnitude. Is that true? No, that's false. And remember, where is the when the capacitor is charged, in what direction is the electric field? In this case, for example. How does the electric field come? Huh? This way, right? Electric field points this way. Why is there an electric field? Well, because of charges. Remember, the electric field between the plates is sigma over epsilon naught. So it has this charge, the electric field better be 0 at the moment. Another way to view it, the capacitor stores energy in its electric field, but all the energy is now in the inductor, so there is no electric field in the capacitor. So option 3 is actually not correct, it's wrong. Option 4, I think we said it's correct, right? We said the charge will be 0, right? In the capacitor? Charge in the capacitor will be 0. It says here, the induced EMF in the inductor has its maximum value. Is that true? This one requires something. The induced EMF in the inductor will have its maximum value.
Is it false?
It is false. Why?
Because I thought maybe not
It's the change, yes. So it's the flux is the magnetic field times the area, right? The induced EMF is d flux dt. Now the magnetic field will depend on the current. If the current is maximum, it means here's a maximum. What's the derivative when you have a maximum? 0. That's the maximum. So the time derivative, the current is not 0, the current is actually maximum, but its derivative is 0. So actually, the EMF, when the current is maximum, is what? Is 0. The induced EMF is actually 0 at that moment. The induced EMF is 0. So the correct options are 2 and 4, right? Or 2 and 4. And we have solved this yesterday. We will solve it again, but you may recall this, that the charge in the capacitor was equal to Q initial times the cosine of omega times T, right? And then the current is minus, no, it's actually omega Q naught times the sine of omega. Because the current is the negative derivative of this one. And omega is 1 over the square root of LC. We will derive this soon in this worksheet. Yes, ma'am.
So when the switch is flipped, the capacitor like instantly discharges?
No, it will take time.
Okay.
Yeah. So at that instant, the capacitor is still fully charged. The current is still 0. And then as time goes on, the current will start to climb up and increase, but the charge will decrease.
Okay.
And you can look at the function this way. So here is, before I draw it, can I, yeah, maybe I will draw it. So here's the time. And then on this axis, I'm going to draw the charge. The charge is a cosine, right? Cosine. So you get this. Like that, right? The current is the sine. Sine starts at 0. Right, so I'll make it 9. Okay. Any questions on problem 4? Problem 5 is similar. So same setup. You have a capacitor fully charged, and then you flip the switch, and then you have just the inductor and the capacitor, and the charge flows back and forth. So let's think about that. I'm going to pause here. So, look at figure 1. The current is this way. The current is the flow of pluses. So this side is getting more positive. You have pluses going away, so this is getting more negative. More pluses means a stronger electric field. Stronger electric field means, or more charge on the capacitor, it means the energy in the capacitor must be getting larger. By conservation of energy, the energy has to come from somewhere. It must come from the inductor. So the inductor must be losing energy. If the inductor is losing energy, it means the magnetic field in the inductor is what? Getting smaller. Okay. So that's that. Now what's the difference between figure 1 and figure 2? Is there a difference? They're actually the same figure. Well, just go behind the board and look at figure 1, you will get figure 2. Yeah? Or take figure 1 and just rotate it this way. And you will get figure 2. So there is no difference between them. You get the current this way, so you're putting on more pluses here, so the electric field here is getting larger, so the magnetic field must be getting smaller. Okay. So notice how sometimes it's convenient to think of energy. Sometimes it's convenient to think of charge. Not because they're just contradicting or you get new information, it's just more convenient to think of it in a certain way. Just like earlier when we did the units for the inductance, Henry's, it was nicer to just look at the flux and think about related to Faraday's law to get the units. Okay, let's look at problem 6, which is essentially kind of similar but different question.